Okay, hello everyone, and welcome to our second Oxford seminar. This week we'll be hearing from Owen Lynch, who'll be talking about Markov semigroups.
Okay. The title of this talk is Markov semigroups from 1,000 miles away.
May I request that you write in 2 square sizes?
You may request that. Is it
It'll
really
be better for the recording.
It'll be better for the recording. Okay.
Yeah.
I think that's actually big enough.
We can see it here, but if we upload this to YouTube, I think it's not public.
Okay. Okay. Fine. Okay, Markov so my title will be the smallest thing. So this is going to be a quite haphazard overview of Markov semigroups. I'm not going to get into the analysis. And so some of what I say is going to be morally correct, but probably factually wrong. And let's just get started. So Markov semigroups, it's a dumb name. It's kind of a weird field. But really all it is various morphisms from B R greater than 0 into categories C. So what is this? So B R greater than 0, this is the de-looping of the positive reals with addition. So this is the category with a single object whose morphisms are positive reals. And C is some category. So an example category C that you might care about would be C equal fin stock, which is the category where objects are finite sets and a morphism from X to Y is a function X to delta Y, where delta Y is the collection of probability distributions. Probability dists. So a Markov semigroup and I'm just going to stop calling these Markov semigroups. So Markov semigroup is like for one particular C. But really, like the theory of Markov semigroups really does use like a variety of different Cs. So I think it's useful to just, abstract to this context, and we'll just call them positive real actions because that's what they are. So a positive real action in fin stock consists of P sub T which goes from some fixed X to delta X for every T in such a way that like P sub T composed P sub S equals P sub T plus S. So you can think about this as given any length of time, I can evolve the system stochastically for that length of time in such a way that if I evolve the system stochastically for length of time t, and then I evolve it for length of time s, that's the same as evolving it for the length of time t plus s. So let's give an example of this.
Sorry, can I ask first,
Yeah.
what are the identities on fin stock?
The identities on fin stock, you send a element of the finite set to the Dirac distribution on that element. Yeah. And so let's give an example. Suppose I have a graph like this, and then I have a happy little bug. on one vertex of the graph. And this bug is going to, hang out on this vertex for an exponentially distributed length of time, where it is exponential. The exponential parameter is given by the out degree of the edge. So if the bug has more options to leave the edge, then it will leave faster. And then once it decides to leave, it jumps uniformly on the edges available out to it. So this is a random walk on this graph. And this gives a positive real action on fin stock, which like P sub t sends V in the set of vertices to the probability dist of where the bug is in t seconds. So, but what is this mathematically? Well, mathematically, we can compute out P sub t by first looking at first recalling a couple things. So first of all, a map x to delta y in finstock. This is an equivalent to a matrix.
Now off the screen.
Oh, okay. This is equivalent to a matrix which where this dimension is y and this dimension is x. And the idea is for each of these columns is the probability distribution for a specific x. But what does this do as a linear transformation? It says that if I have f in R to the y, this matrix, which I'll call like T, then T of f is, if this original thing is called P, this is the expectation if TF of x is the expectation if y is distributed according to P of x of f of y. So a map x to delta y, this is equivalent to a certain class, which we'll get into exactly what that class is, of linear transformations from R to the y to R to the x. So what is this class of linear transform? Let's actually just go through an example and try and build up from this perspective the random bug example. So in order to do this, let's see. Well, maybe I'll just go to a new page. We first have to start with the graph Hamiltonian, or the graph Laplacian. I called it the graph Hamiltonian because it actually serves as a Hamiltonian in a certain sense. But anyway, so what is a graph Laplacian? So if we have a graph G, which maybe is given by something like this. Then the graph Laplacian is a V by V matrix, where each of the diagonals is the out degree of each vertex. So in this case, that would be 2. And then from here, I have 1 out degree, 1 and 0. And then the off diagonals are given by the number of vertices, by minus the edges going from here to here. So it's going to be something like -1, -1. Here is 0, 0. And then I have a -1 here and a 0.
You need like your vertex set to be totally like ordered.
Well, you need to pick
Or like
an
you
order.
pick an order.
Yeah. Yeah, I mean, you know, actually, as a linear transformation, you don't need to give an order. But if you want to write it down as a matrix, you have to give an order. And let's call this L. Now, it turns out that if phi is psi is a prob dist for my bug, like if I think at a given point of time, then phi evolves according to the equation d dt phi equals L phi psi, yeah, whatever. And now this is solved.
When you say it evolves according to this, is this like using the model of this like exponential decay, then
Yeah,
uniform
exactly.
choice? Okay, so it's like, okay, so it's like assumption about, yeah, this isn't
Yeah.
a general statement for any probability.
No. It's if my bug is moving according to this random rock, then if you just like think about how the probability distribution of the bug evolves over time, it's according to this differential equation.
Right.
And the solution to this is given by phi of t equals e to the t L phi of 0. Where this is a matrix exponential. So where like e to the like a is just given by this infinite sum n equals 0 to infinity a to the n over n factorial. And this, you know, when does this exist? Well, it turns out that for graph Laplacians, it always exists. So that's good. In general, it might not always exist. But so this is a matrix, and that is our Markov semigroup. So specifically, we have P sub t equals e to the t L, which is, you know, it goes from R to the V to R to the V, which is equivalent to V to delta V. Which is not true for all linear maps, but for a special class that we'll get into later, this will be true. And so we might ask, so if we have, you know, we managed to, we started with this special setup, which was like a bug jumping around a graph. And we ended up defining the Markov semigroup as this exponential from this L, which which sort of generates the entire process. You might ask, is this the only way to get a Markov semigroup? And the answer is more or less yes. So given any Markov semigroup PT, where we're going to view PT as going from Rx to Rx for every
So just
T.
to be clear again, so like we are fixing like C is equal to fin stock. Like this isn't like a general
Yeah.
thing.
I'm just doing everything in fin stock for now. We're going to get to Banach spaces
Okay.
later, but which is where the classical, which is mostly what people talk about, but you can do everything in fin stock. So we can try and define L equals lim T goes down to 0, because notice T can only be positive, can't be negative, of so this is going to be L of F equals lim T goes down to 0 of P sub T F minus F over T. Just a happy little derivative. But the point is that, the limit of this is going to be a linear transformation from Rx to Rx. And now, let's talk a little bit about what precisely what linear transformations end up corresponding to Markov kernels, and what linear transformations correspond to generators of those of Markov semigroups. So we sort of hinted at this before, where when we have P goes from X to delta Y, the corresponding transformation T, it has its columns here are all probability distributions on Y. So in Finstock, a linear transfer, you can just see this. Generally, a linear transformation corresponds to a Markov kernel if and only if each of its columns are all positive and sum to 1. And similarly, and now I may have got this backwards, actually. I think that I actually want the transpose of this. So L transpose is this. But for Finstock, so and in the case that this is true, that they're all positive and sum to 1, we call this a stochastic matrix, which is different than a random matrix. But then for the generators, they have to all of the columns have to sum to 0. So you can see by the way that we've set this up, then like it's the out degree, and then the other columns are like the actual edges coming out of it, so that it's always going to have to sum to 0. And one intuition for why that has to be the case is that, this is telling you how probability distribution is evolving, and it has to stay a probability distribution. So it has to be sort of mass preserving. And the fact that it sums to 0 is connected in some way to that mass preserving requirement. Okay. So that's essentially the easy case of Markov semigroups. We start with a functor from B from the monoid of positive reals into some category C. If C is Finstock, then this can be interpreted as like a collection of Markov kernels. This dually is equivalent to some collection of linear maps. And And we can take, once we put them into linear maps, we can take the derivative at time t, and that generates the whole process. So now let's go into the infinite dimensional. The bug's still quite small. But we could have the bug's world is big, exactly. So yeah, so actually that's maybe a good example to start this off. So suppose we have a bug on the integers. I'll draw the little bug. Little. Okay. Jumping around on the integers. So how do we talk about a Markov semigroup for this? So in the stochastic domain, or in the stochastic sense, this is quite straightforward. So all we have is a collection of transition kernels, PT, goes from Z to probability distribution on Z. Great. But now we have to work with not just in happy little linear algebra, finite little linear algebra land, we don't have to care about metrics or continuity or anything. But now when we dualize to T sub T, this is going to go from B Z to B Z. And this is the Banach space of bounded functions from Z to the reals. So what is a Banach space? A Banach space is a normed vector space such that the addition and scalar multiplication operations are continuous with respect to the topology induced by the metric of the norm. And what specifically is what is the norm? So the vector space structure on bounded functions from the integers to the reals is just pointwise addition. What is the norm? Well, it's just the sup norm. So norm of f equals sup over I in Z f absolute value f of I. And because these are bounded functions, this sup norm is always less than infinity. And so now this linear transformation here is what properties now characterize it as being as coming from a Markov kernel. Well, actually, in this case, it's pretty easy because we have sort of Dirac distributions. So in this case, we could actually just say that for each I in Z, we have delta I, which goes from Z to the reals, and wherever T sub T of delta I is going to be, this is going to be in delta Z, which is, of course, a subset of BBZ, right? So this is actually sort of a bad example because when is this, does this correspond to a Markov kernel? Well, it's just when, oh wait, that's actually just not true. Sorry. Okay, I thought this was easier, but actually we need to go to the general definition. Sorry. So the when is this a Markov kernel? So first, it's a contraction kernel. Def a contraction from B to W, Banach is a linear map. Let's say T, V, W, such that TF less than or equal to F for all F in V. So this is one property that T sub T has to satisfy. Another property that has to satisfy a unit preserving map B to W. Well, in the concrete case, when V is like BBX, then we have a 1. So 1 in V equals const 1. So let's just talk about this in the case where V is the Banach space of bounded functions to X. So a unit preserving map sends 1 to 1, and then def a positive map sends everywhere positive elements of BBX to BY to, sorry, everywhere positive, or really everywhere non-negative.
Does everywhere here mean like non like dense, like measure 0, not, or like,
Well, so in general, X and Y are measurable spaces, so it actually does mean everywhere.
oh, okay, okay.
Yeah. Because there isn't a notion of null set. So Markov kernels X to delta Y, where X and Y are measurable spaces, are in 1 to 1 correspondence with linear contractions BY to BBX that are unit preserving and positive. And now let's build up a little intuition for why this is the case. So if we start with a Markov kernel P here, then the corresponding contraction T is again defined by TF
You have to move the page down.
equals expectation y. Well, I made the same mistake again. TF of x equals expectation y p of x f of y. And why is this a contraction? Well, it's a contraction because when you pass something through a stochastic kernel, it only kind of smooths out. So it's you can't, its supremum can't ever increase. That's sort of the intuition there. Because like any point in for any point in X, the value at that point has to be a convex combination of the value at points in Y, and all of the convex combination can never be greater than the supremum. So that's why it has to be a contraction. Why does it have to be unit preserving? Well, just obviously the expectation of 1 is 1, right? And then finally, it has to be positive because the expectation of a function that's positive everywhere also has to be positive. And moreover, you can see that like for a general measure, if P were not a probability measure, then wherever this sends 1 has to be the total mass of the probability measure, of the measure. Because yeah, you're just integrating 1 across the whole measure. So yeah, it has to be 1 because that says, you know, probability measures are measures that sum to 1. And then positivity corresponds, like if it weren't positive, like a linear transformation here could correspond to like a signed measure. But probability measures are not signed measures, they're positive measures. So
yeah, just to clarify, I'm sort of with it here. We have E is an algebra structure for delta on R.
Yeah, that's right.
And so what we're doing here is we take this map, we take P from X to Y, we take our function from Y
X
to
to
R,
delta Y.
X to delta Y. We take our function from Y to R.
Yeah.
That gives us a function from delta Y to delta R.
Right.
And then we sandwich that by P and the expectation.
Right.
And that gives us a formula for T.
Right. Okay. And so now that we have this sort of abstract, we have this characterization of Markov kernels in terms of contractive unit preserving positive maps, we can do the exact same thing. So if we have a Markov semigroup, PT goes from X to delta X, then we can make a what is actually, now this is the actual thing that people call Markov semigroups in the literature. T sub T goes from BBX to BBX. And now we can do the same thing that we did before, where we can define L of F, and I'll say L of F of X. So L is going to be another linear operator from BB to BBX to BBX. L of F of X is just lim T goes down to 0 of T sub T f of x minus f of x over T. But now this is where the analysis starts to get hard, because in the happy finite case, this produced an actual linear transformation. But here, in general, this linear transformation will only be defined on a dense subset of BBX. And so there's a whole theory in functional analysis of what are called dense open. Dense open, yeah, I believe so, yeah. There's a whole theory in analysis of what are called unbounded operators, which are operators like this that are only defined on a dense open. That is quite subtle and quite tricky, and because this is a 1,000-mile view, we're not going to get into that. But now the question is, what linear map? So if we go, we can take any Markov semigroup and find its generator via this limit. How do we go backwards? And the answer is the Hille-Yoshida theorem. So this characterizes what linear operators are the generators of actually not Markov semigroups, but contraction semigroups, which are a larger class. They are just like, functors from the monoid of reals into the category of Banach spaces and contractive linear operators. But that's already pretty good, because the tricky thing is not figuring out whether or not, you can just look at your contraction semigroup and ask whether or not this is whether or not the contractive semigroup is Markov. The tricky thing is figuring out which linear operators can you exponentiate in the first place to create the semigroup. And the Hille-Yoshida theorem essentially boils down to two things, to two conditions. Conditions on L. The first condition is the positive maximum principle. This one is a little bit weird. There's not a great intuition for this, but it's basically if F is in the domain of L, so because L is in general an unbounded operator, so it only has a dense open domain, with x0 a maximum, then L f x0 is less than or equal to 0. That's kind of weird. But I'll talk about maybe a possible intuitive interpretation of this in a bit. But the second one is more intuitive. The spectrum, the eigenspectrum of L is in the negative half plane. So specifically here.
So just to be clear, the positive maximum principle says that LF at the maximum is negative. Or like
Yes,
it's
yes.
non-positive. Okay.
Yes. Yeah, it's kind of weird. I don't know why it's called. I mean, it's clearly connected to maximums, but I don't know why it's the positive maximum principle. But yeah, anyways. But the second one, which is the eigenspectrum of L, is in the negative half plane. This is more intuitive because when you have e to the TL, where is the eigenspectrum?
It's the negative real part?
Yeah.
Okay.
Yeah.
Okay, sorry, but is everything over R?
Well, yeah, but something over R can still have a complex.
No, but I was just wondering like what
Yeah.
everything's over R.
Yeah. E to the TL, the eigenspectrum of this is going to be given by like e to the t lambda for lambda in the eigenspectrum of L. And where is this going to map? Well, it's going to map into the interior of the unit disk. Oh. Because yeah, e to the t lambda for lambda with non-positive real part is going to be inside. And intuitively, this is the condition for being a contraction. So okay. So the Hill-Yoshida theorem is very important. Let's see. Oh, I'll say a brief connection to quantum mechanics. Where in quantum mechanics, you have the exact same phenomenon, except you have maps BR into Hilb with unitary operators. And in there's a theorem in quantum mechanics called the Stone theorem, which I can't remember totally, but one of the conditions for the Stone theorem is that the eigenspectrum of L is purely imaginary.
So you land on the unit disk.
And so exactly, you land on the unit circle. And this, yeah. And this corresponds in the Schrodinger equation. This is why you have d dt of phi. Wait, psi equals negative I, blah blah blah, constants. Who cares? H. So H is has to be self-adjoint. It's the observable that gives you the energy states of the system. Self-adjoint means
L in this?
yeah. Oh, sorry. No, H is not L. Negative IH is L.
Oh, okay. Yeah, sure.
H is the observables. Its eigenspectrum is purely real. Because it's self-adjoint.
Okay.
When you multiply it by I or negative I with convention, then its eigenvalues become purely imaginary, and then it's suitable as a generator for a unitary. Yeah. So now let's actually try and from the Hill-Yoshida theorem gives sort of fairly abstract conditions on L. What does that actually boil out down to? Well, that's given by the Courrèges. There's a Courrèges theorem, which gives a much more explicit characterization. So 7.2.9 of apple bomb. The Applebaum is a great book on if you just search Applebaum Markov semigroups, you'll find a great book. So let L goes from C infinity RD to F RD. So this is specifically basically this is saying like, okay, in general, L is going to be defined on a compact subset, or sorry, not on a compact subset, on a dense open subset of bounded functions from RD to the reals. Like most of the time, that dense open subset is going to include all smooth functions. And it's going to send those smooth functions to just some function from the reals to the reals. F of RD is the space of all functions from the reals to the reals. And then L satisfies.
So is this it's compact support? What's the tiny c?
Yeah, I think compact support. Yeah. If L f of x equals negative cx fx plus sum over I equals 1 to d bi x di fx plus ij equals 1 d aij di dj f of x plus integral over r d f x plus y minus y minus sum over I equals 1 to dy sub I di f x 1 y less than 1 of y v x dy, where cx bix and aioijx, these are all these are all like defined over RD, and then Vx dy is what's called a Levy measure. But the point is, this basically says that, like, in theory, something that is a contractive. So yeah, not all of these will end up being contractive semigroups, because this is just about the positive maximum principle. So it also has to have this linear operator also has to have negative eigen spectrum. But it says that, like, this is a fairly strong result, because it really cuts down what the linear operator is. Specifically, it's only going to depend on the second derivative of f. It can't depend on any higher derivatives, which I think is very interesting. And if you look at this essentially says that all of the positive maximum principal operators are going to be something like a drift diffusion jump processes. I think that in practice for a contraction semigroup, C is 0, but I'm not sure. This one has confused me, but these correspond to drift, diffusion, and jump. So yeah, so I think that's kind of interesting from these like this very abstract characterization of like Markov semigroups. We get that, okay, well, all of the interesting ones come from stochastic differential equations with like a drift, a diffusion, and a jump term. Okay, so that's pretty much the end of the big overview. And what I want to end with is two things. One, so the classical
A little bit more.
theory equals, they use BBX, right? But they use BBX, but they don't just care about it as a Banach space. They also care about what the unit is, and what are the positive elements. And so that depends on that's not just an abstract property of the Banach space, that depends on the Banach space being specifically a Banach space of functions. But there is an abstract algebraic structure where that you can derive positivity and unit from. It's a C-star algebra, where a C-star algebra is a Banach space that's also a algebra, like a real algebra, with unit. So it has a specified unit, and that unit is characterized by being multiplication. So I'll say why not C-star? And positivity is given by the operators that are the square of some other operator. Or sorry, like A is positive if A equals, B star for some other B.
People say that about matrices.
Yeah.
A matrix is positive if it's this. Yeah.
Yeah. And it turns out that if you think about C-star algebras of measurable functions to the complex numbers, then this is exactly positive operators. So if we move to C-star algebras, then we can sort of drop the underlying spaces, because there's sort of an intrinsic notion of there's already an intrinsic unit and an intrinsic notion of positive. The interesting thing, though, is that the maps that we choose don't preserve the C-star algebra structure. They just preserve positivity and unit. So one idea I've had,
These are, just to check, these are commutative real C-star algebras.
commutative, or complex.
Okay.
Complex is fine, but commutative, so it seems a little bit strange why do we have the whole C-star structure around? Another approach would be to say that we could instead go to what I call Banach cones, where a Banach cone is like a cone equipped with a norm, and we could take the cone of just all positive valued functions from X to the reals, which sort of is just the positive elements of a C-star algebra. And it's like, that is really the structure that matters for Markov semigroups.
So is it a cone equipped with a norm?
Yeah.
What's a cone?
So a cone is like a vector space, but with only scalar multiplication by positive reals.
Okay.
And it's, you only have a monoid of addition. You don't have minuses.
Okay, and you think we can recover the notion of unitary?
Oh, right, you have to add some notion of unit there
Right,
as well.
okay.
Which is a slice under the positive reals. As a
Yeah,
cone, as a
yeah.
cone, as a normed cone,
Okay,
yeah, but not a cone, if you will.
yeah. Right. You have to know like what are the constants for every, yeah, exactly. So that's sort of interesting to me. So first of all, why not Banach cones? Because yeah, every map between Banach cones is automatically positive because you can't send it to anywhere else. And then the second, so this is like sort of question 1.
And is the point that the maps of Banach cones correspond to the contracting maps?
Yeah.
Okay.
The second, oh, sorry, no. They correspond to the positive maps.
Okay, so are we rejecting?
It's contracting. Yeah, you have to say a contracting map of Banach cones, etc. Yeah, it has to preserve the norm. But yeah, I think once you're talking about Banach spaces, like all maps should automatically be contractions. Just kind of like how the natural map for a metric spaces is.
It's generally but like you pick one of two things, because like if you have
You should also say Lipschitz. Yeah.
no, but also like if you take Banach space, it's like it's not bi-complete as a category, but if you take short maps, contracting maps, you call them, it is. But the other option is you just take pre-sheaves on all maps and then look at day convolution, get it by a cosmos this way. So like there's a choice.
Okay.
So like some people are like, yeah, they should always be contracting, but there are other options.
Could you say that again? That last sentence?
Take like pre-sheaves on Banach with non-short maps, and then look at the symmetric monodal structure coming from just day convolution of pre-sheaves. This is a bi-complete symmetric monodal category, like in a way that Banach isn't, unless you take short maps. Yeah.
Cool. So the second question is in synthetic differential geometry, a vector field is a map from x times d to x, where such that if you go from x to here, this commutes. So where d is the space of first order infinitesimals. So d equals spec of r x squared. And you can think about this, it's like, this is equivalently d to x to the x. If you curry it, and this sort of says, like, for each infinitesimal, I'm going to give you a little movement of this tiny little movement of the space. But then such that when the infinitesimal is 0, so this map is like, x maps to x0, I get the same element.
You can put the triangle on the left-hand side, but the point mapping to D0 and the point mapping to identity. Yeah.
0 ID. Yeah. So if we flip that around into algebra world, we have a C-star algebra A, then this should, instead of from x times d to x, should correspond to A maps to A tensor R, and I'll actually use D here instead of X. I'll use R D mod D squared. Now, by algebra, this is equal to A adjoin D mod D squared. Now, of course, this is not a C-star algebra because you have to figure out like what's the norm structure on this, right? So this is dream math. But so this is actually not that hard to work out. This has to be something like A maps to A plus LA D. Like all maps are going to have to be of this form. Now I've written L here suggestively because what I think should turn out is that L has to be the generator, or should be the generator of a Markov semigroup. And there's a intriguing thing that maybe points in the right direction why this might be on the right track, which is you think, what does it mean for such a map to be positive? Well, if A is sort of a C-star algebra of functions on a space, then that means
Scroll down.
yeah. Then that means for all x, A of x greater than or equal to 0 implies that A of x plus LA of x d greater than or equal to 0. What does this mean? What does it mean for an element of this of like r d mod d squared to be positive? Well, the intuitive thing is to say, if this is positive, then great, we're done, right? Otherwise, if this is negative, we're also done, then it's negative. If it's 0, then we go into here and we look at whether this is positive or negative. And you're saying, like, to the first order of magnitude, we care about whether this is positive or not. But if it's 0, then we go check here. And so for this to be positive, it has to say that, like for this map to be positive, we have to say if A of x equals 0, this implies that L of A of x is greater than or equal to 0. So this is not the positive maximum principle, but it is what's called almost positivity. I did not make this term up. This is like a key lemma in the Corrèze theorem, is showing that a positive maximum, an operator satisfying the positive maximum principle is almost positive. And then there's also a result that says like almost positive operators are all second order, which means that only this, we only have differentials showing up in this up to second order. There's nothing higher. So, I don't really have so much time to work on this stuff. This is mostly coming out of stuff that I was thinking about like maybe like 8 months ago. But this is really tantalizing to me because the types map out where such a map is actually just specified by a linear operator on A. And that linear operator is like, kind of it has to satisfy this condition, assuming that positivity is defined in this way, that is like super connected to the Corrèze theorem and the Hilliard-Yoshida theorem. So that's very exciting to me. So that's pretty much the end of the talk.
Okay, great. Let's thank Owen. Now, are there any questions?
Yeah, really cool. I'm excited about this last part. I have a question in a Banach space, right?
Yeah.
The norm's positive definite,
Yeah.
right?
What do you mean positive definite? It's not a matrix.
It's not a what do I call this? If the norm is 0.
Yeah, then the thing has to be 0. Yeah.
Right. But what if the norm was 0, it had to be nilpotent?
Yeah. 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 Yeah, that would be cool.
Is there a like, how does that connect with you're saying weaken the notion of Banach space?
Oh, then if you
Weaken
take
the notion of
the
C-star
norm on the
algebra.
right to just be the norm of A. And then if that were 0, then A would be 0 because A is a Banach algebra.
Right.
But
Yeah, well,
then
let's-
we would be left
you
with
have
an
to- you have to-
infinitesimal on the
In
right.
order to talk about nilpotency, you have to be working in a C-star algebra, because otherwise you don't. have
Sorry, yes, a
nilpotency.
C-star is what I should be saying, a C-star algebra.
Yeah.
So then you can say on the because you have a C-star algebra structure. On the left, you have if the norm of A, like define the norm to just ignore the infinitesimals, they have 0 norm.
Yeah.
And then you like take that norm on the right. That is going to be like I think you by Cauchy-Schwarz, that's the norm of A. If the norm of A is 0, then A is 0, and that's just an infinitesimal. But then it's just L of, I guess it's L of 0, so it kind of dies too. But like if it's A plus PD, like a general element, right?
Yeah,
Then it's
I mean,
then
the
A
other-
would
the other
be-
option
the
is
first
to
A would be
take,
0,
like,
but then the second.
norms in vinyl algebras.
But like morally infinitesimals have zero
Zero.
length in a way.
Right, so just weakening the condition to include these infinitesimals.
Yeah,
Okay.
to allow for nilpotent elements.
Yeah.
Yeah, and I mean, yeah, it's a so right, a lot of cool ideas.
I think for the sake of the time, we will end the recording. Thank you all for coming.